It's my great pleasure to welcome Dr. Wojciech Samek. He's an extraordinary researcher and speaker. He has founded and is heading the machine learning group at Fraunhofer Heinrich Hertz Institute. He's so experienced, so I'm speechless. And I have already posted a link to one of his book. It's about Explainable AI, extraordinary book. And I think that it will be a great event today. So, Dr. Wojciech Samek, the virtual floor is yours. Thank you very much.
Thank you very much. Thank you very much for the invitation. So I'm very happy to give this talk. So it will be about explainable AI. So mainly about our research here in Berlin, but also I will cover some other topics. So already since the beginning, people considered machine learning models as black boxes. So even in the original paper of Frank Rosenblatt in 1957, when he described the perceptron, he said that we might consider the perceptron as a black box. Although he meant it in a slightly different manner, is this idea that we have some machines, some black boxes which are doing something with our data has been there from the beginning. And things became much more complicated after that, because our models became larger, especially in the last 10 years or so. We are having models with many layers, with many parameters. So it totally became very difficult to understand why they behave as they do, what is the reasoning of these machines, why they classify, for example, an image in the way they do. So there was always this wish to understand this. So in the 70s, people were trying to build these expert systems where they kind of encoded by hand these kind of rules. Today, we are much more data-driven, but still the wish is there to understand our models. And yeah, I mean, we have seen a lot of great successes in the last years in many domains. Deep neural networks and complex machine learning models have been performing extraordinarily well. So, of course, in the image domain, but also in understanding speech, understanding text, playing games or medical applications. And the more we are using these machines in this more sensitive applications, the more important it becomes to really understand what they are doing, to make sure that they are behaving correctly, to be able to validate their decisions. So the question which comes up when you use, for example, machine learning in the medical domain is, can we trust it? If it's a black box and we don't really understand what's going on, so how can we know that it's doing something sensible? And of course, the standard approach is to have to minimize some error, for example, on some training data set, and then like validate things in a test data set to see if your model performs well. But the question is minimizing the error a guarantee for the model to perform well in practice? And I will show you some examples from our research that it's not. So I will show you some examples that we really need better understanding of what our machines are doing. So like just minimizing the error, just testing performance may be very misleading. So why do we need interpretability or explainability? To foster trust, to be able to verify a prediction. For example, in the medical domain, the AI system could be like an assistant for the medical doctor, but the medical expert would like to take the decision on his or her own. So just having like the classification result maybe not very informative. So the medical expert would also like to know the reasoning of the system. So in these domains, it's quite important to get trust and being able to verify. Of course, there are some legal aspects to it. The GDPR explicitly talks about the right to explanation. So if people are subjected to the decision of an autonomous system, of a machine learning system, they may want to know why this decision was taken in this way. For example, in order to rule out that there has been some discrimination. They may want to know also, like they may have some legal right to know which features have been used, what kind of was the basis for the decision. So there is some right to explanation to it. So in many of these fields, if you're using machine learning, there's companies and this people who are using these machines tell me that these machines have to be explainable, otherwise it's useless, because they have to be able to explain the decision making. In order to retain human decision in the loop, to assign responsibility, for example, in the medical domain, it's important to be able to interpret, because in the end, maybe the medical doctor will make the decision, not the machine, but the machine will just provide some additional information to the medical expert. A very interesting domain is that if you are able to understand your machine, you may also learn something from it. So there is this famous Go game between AlphaGo and the human champion, and another Go player analyzed the game and said to a move which was done by the computer, he said, "It's not a human move. I have never seen a human play this move." So apparently the computer, the machine learning system has invented a new strategy, and the better you understand the reasoning behind it, the motivation behind it, the better it is for a Go player, for any other human player, because then we can learn from the system. The things become even more critical in physical, biological, chemical domains, where you want to understand nature. You're not so much interested in the prediction itself. You are much more interested in finding the causes, for example, the causes for a disease, which genes are linked to a disease. And in order to find out, you need to understand the mechanisms. So in the future, it will be that we will have a lot of data. We will have very smart machines. They will learn from the data, analyze the data, and then with explainability, with interpretability, we will be able to make sense of the results and maybe learn something about the biology or the chemical mechanisms and so on. So this is something which is very, very important. And finally, also, if you're an engineer, you may want to have your models be interpretable, because the better you understand your models, the better you understand the deficits, the things which do not work, the better you can improve them. So in future, I mean, already we are doing it already now, that we bring in human experience when training models. But the more transparent these models are, the better you can use human intuition, human experience to improve things. And I will show you later some applications where we use interpretability to improve our models. Okay, so what will be covered today? We will talk about explanation methods. So what do I mean by that? I mean that we have some machine learning model, a deep neural network, which is classifying this image as a pool table. And we want to know why this given image is classified as a pool table. So we want to have this explanation, these heat maps, showing, in this case, these heat maps show which pixels, which features in the image were mainly responsible for the classification decision. So we see that the shape of the pool table, the balls, the sticks were quite important for the classification decision. So the background was not so much linked to the class pool table. So you may look at it and verify these kind of explanations. Since nowadays we have a lot of different XAI techniques, there are many variants. I will also tell you about some theoretical framework, how to analyze methods. We will also compare a few of these methods and see and see how we can evaluate explanations, how we can compare XAI methods. Another very important topic, which I'm very interested nowadays, is what can we do with these explanations beyond just looking at them? How can we use them to, for example, improve our models? Can we use them to prune our models? I will give you some applications. And also another topic which I'm also very interested in is to explain more than classifiers. A lot of this prior work has been about explaining deep neural networks classification models like VGG or GoogleNet or AlexNet. But there is much more in machine learning than classifiers. There are other types of problems, and we may also want to make methods in these domains explainable. And we will see that we can transfer some of the techniques developed for classifiers also to the other domains. Okay, let me start with explanation methods, with the methodological aspect of this research. Yeah, there are various ways people have addressed to explain predictions. So keep in mind that we were talking about explaining individual predictions, like with the image and the pool table, because there is also other types of XAI research, which, for example, tries to understand the representation of a neural network, tries to understand which neurons are important for encoding a concept. There are many other directions, but here we are mainly focusing on explaining predictions. So in this domain, there has been many different methods. So one type of method, which is also very old, I guess it's even older than 2014, perturbation-based approaches. So I will tell you in a minute what they do. There are also like function-based approaches and surrogate sampling-based approaches and structure-based approaches. So let me give you a very, very short idea of what these different classes are doing. So perturbation-based methods, they take an image, for example, and perturb it in some ways, and then they measure the reaction of the classifier of the model to this perturbation. And they do it over and over again. And from this, they identify the relevant information. I will show you in a second how this looks like, but this is the idea. So you perturb, you measure the reaction, then you perturb again, measure, and so on, and then you construct these heat maps. Another class of methods are function-based approaches. Here, the idea is that you treat the neural network as a function. And then you compute some simple quantities on this function, for example, a gradient. And from this gradient, you construct explanations. So keep in mind the perturbation-based approaches, they are model agnostic. So you don't need to know anything about your model. You just need to be able to measure the reaction, the classification score. Function-based approaches, you just need to observe some gradients. You don't need to know anything about the structure. Surrogate-based models are also model agnostic. Here's the idea that you locally approximate a prediction using a simple function, for example, a linear function. which is interpretable. And then once you have this approximation, you explain the simple function. So instead of explaining the complex function, you explain the simple function. But of course, for every prediction you make, you need to do this approximation, which can be like computationally heavy and also has some other disadvantages. And then finally, we have the structure-based approaches. This is methods which I'm mostly interested in. And here the idea is that you use structure. So you utilize structure to make the explanation simpler. So instead of explaining the whole thing, you kind of use structure of the neural network. And then, for example, you explain each layer by layer. And after that, you meaningfully aggregate things. I will show you in a second what this means. But this is our methods, which I was co-developer. Layer-wise relevance propagation does exactly this. So the structure-based method, the main advantage is that you use structure, therefore you make the explanation problem easier, but of course you need to know the structure beforehand. Okay, perturbation-based. So assume you have an image of an castle, and the neural network tells you, okay, this is a castle. And what you can do is you can mask different parts of the image and measure the reaction. And you will see that if you mask the lower left part, it's still classified as a castle. If you mask this middle part, it's still classified as a castle. But if you mask the castle itself, the neural network is confused and it's not classified as a castle anymore. So from that, you can derive that this area which you mask was important for the concept. Very simple idea, but it's quite slow. You need to mask, you need to put the windows all over the place. It assumes some locality because sometimes maybe the concepts which you want to classify are not local. So maybe it's a composed concept. So you would need multiple windows to mask. And also the perturbation may introduce artifacts. So assume you would, instead of using this dots, which I used here, assume you would use a gray window, a gray square, then maybe a gray square on a hill would still be classified as a castle. So the masking could be due to some artifact, it would not work because a gray something on a hill looks like a castle. Okay, so it's perturbation based. It's very simple, and still some people in some communities are using it. But I think in machine learning community, people now realize that they have some heavy disadvantages, and there are better techniques. If you would ask a mathematician, if you would say, okay, how can I explain neural network predictions? And he would probably say, okay, a neural network can be regarded as a function, complex function. And then there is something like a Taylor expansion, which you can perform. And in Taylor expansion, you have to choose a root point, x tilde. And if you use a root point if you use a root point in a smart way, then f of root point cancels out, and you will be left with some linear part, first order terms, and some higher order terms. And the first order terms you could use as relevance measures. So there was a question, but I will answer it in a second. Let me first move through this Taylor expansion. Yeah, so so there's a key insight is here that if you choose a good root point, then maybe you have a good decomposition. But unfortunately, the simple Taylor expansion is not a good explanation method because it's very hard to find a good root point. Because if you would choose, for example, a root point which is too far away, for example, 0 in the origin, it would not be a good approximation to the function you want to explain. So in principle, you would need to find a root point which is close to the, for example, an image space, close to the image you want to explain, but does not have the concept which is responsible for the classification. But this you don't know, so it's very hard to find a good root point. Another disadvantage is that you use, in the first order terms, you use the gradient. And there has been some research showing that for very deep neural networks, gradients are not really informative. There is a phenomenon called gradient shattering, which makes gradient-based explanation methods very noisy and not so informative. Okay, so there was a question about masking by deleting data from images and not overlaying another picture from an image. Yeah, I mean, there are many different works on this, how to mask. So of course, this is like a very trivial example, which I showed here. People also tried to have some meaningful perturbations where you kind of have a deletion process, which makes your image still look realistic. But I would say many of these methods still have these disadvantages. They are slow. They assume some kind of locality. And even if you use some optimization procedure, you are not sure that you are not introducing any artifacts, although you're doing the best not to do. But of course, I mean, one advantage is that it's model agnostic, for example, so you don't need to know anything about the model itself. Okay, another variant. So the root point. I mean, in Taylor expansion, this is like the general form of the Taylor expansion. So you have f of x. If you think about a function, it's f of x. Then you can approximate it as f on x tilde plus some sum. So the sum here goes over the dimensions. So for example, over all pixels. Then you have like some gradient times xi minus xi tilde plus some higher order terms. And the trick is that you can have different decompositions based on how you choose the x tilde. And since you want to have a decomposition in the form that you want to decompose the prediction f of x, you want to choose the x tilde in a way so that f of x tilde is 0. So you want to choose x tilde so that f of x tilde is 0. And there are some trivial solutions. If you have just like a radio neural network without bias, for example, you can just take the origin, the 0 as a root point. But it will not be very good because it's very far away from the real image you want to explain. So the better approximation you get, the closer your root point is to your point which you want to approximate. But yeah, so there's a question. These high dimensions, it's very hard to find a good root point. But also a second disadvantage is the gradient. There is this gradient shattering, which makes things also complicated. So yeah, gradient times input is a method which was also quite popular, and it can be reduced to this Taylor decomposition and the perturbation. So for certain cases, you can regard gradient times input as a special case of the other ones. And the cool thing is here that you don't need to optimize. You don't need to find a root point. You don't need to delete all over the place, but you have just like in one pass, you have the solution. You just compute the gradient and multiply it with the input. But as I said, I mean, already here, you have the gradient, and it is known that for neural networks, deep neural networks, the gradient is very noisy, and it due to the discontinuities which you have when you have ReLU nonlinearities, there is this problem of gradient shattering. Therefore, like gradient times input also gives you very noisy solutions. So here you see, for example, that this input has been classified as baseball, but the heat map which you compute is not really informative. So there is no noise all over the place, and it's very hard to understand what the important concept is in the image. And yeah, the reasons is that it's very hard. There is this gradient shattering, and there is some locality versus global variation problem, because you are explaining you are kind of asking the question, not what makes this image, what makes a network classify this image as baseball, but you ask the question, what would you are the gradient computes the sensitivity, which tells you what changes to the image would make it more baseball or less baseball. So this is a slightly different question that you want to have. But I think this gradient shattering problem is also like a big problem which affects all gradient-based explanation methods. Okay, and one solution, as I told you, is layer-wise relevance propagation, which belongs to this is a method which belongs to the structure-based approaches. So it uses structure of the neural network to avoid the gradient shattering problem and to avoid the problem with finding the root point. So it kind of makes the explanation problem easier by decomposing it. So instead of explaining the network as a whole, the whole thing at once, which is difficult, it decomposes the decision function into sub-functions and explains each sub-function. So a sub-function can be like a layer, for example, the mapping from one layer to another layer. And the cool thing is that neural networks are already compositions of simpler functions. So it is not, you don't need to do it in an artificial way, but it's already there. So you have your layers, and in every layer, you just apply some very simple function, just a ReLU and some summing up and some weighted sum and some ReLU, and that's it. So explaining like this ReLU is very easy, but explaining the concatenated thing, explaining everything, is difficult, because the whole thing is complex, but each part on the way is easy. So what you do is you explain the sub-functions, these layers. So of course, in this divide and conquer idea, you need to make sure that when you aggregate things over layers, this is still meaningful. But I will show you in a minute that this is the case. So this aggregation must be meaningful. So we proposed this method in 2015, which was one of the first explanation methods on the market. And the idea is to decompose a prediction function, f of x. So what we wanted is to have a sum of relevance values, so that when you sum up, this equals your prediction. And we wanted every Ri, every relevance value, to measure the contribution of the pixel to the prediction. And of course, the question is, how do we compute these relevance values? And the idea was as follows. So we thought, okay, we have a classifier. We classify this image as a rooster. Some of the neurons on the way get activated because they encode something which is present in the image. They encode maybe a part of the rooster's head, or they encode the flowers in the image, or something else. And then we thought, okay, let's initialize the prediction output as the total relevance which we have. In this case, Rj. This is what we want to explain. This is what we want to redistribute. So we kind of start with the output and then redistribute this relevance layer by layer. And we thought, okay, how can we redistribute it? What is a meaningful rule? And the simple approach which we came up with, we thought, okay, let's take into account two factors. The activation of the neuron, xi. So when the neuron gets more activated, then it encodes something about the image, something which is present in the image. Therefore, it should get a larger part of the relevance. And the other variable is the weight, wij. So if the neurons are connected, if the connection is stronger, then more relevance should flow along these connections. It's like when electrical current is flowing, in some parts, maybe it's flowing, more current is flowing because there is less resistance. So also here you have like the weights which determine how much relevance is redistributed, and you make it proportionally, so you divide by the sum. And we realized quickly that this division by the sum can be problematic because the sum can cancel out, because things are positive and negative, and if you sum them up, they can be very small. So the number can be very small, so you may run into numerical troubles. So we thought, okay, one extension is to just add some regularizer to the denominator. This rule we call epsilon LRP. And another idea was that we individually redistribute the positive and the negative values. So everything which speaks for the rooster, we distribute separately from everything which speaks against the rooster. And then we also have some weighting, so we can weight both parts against each other. So this was the original idea, and if we do this, we get layer-wise relevance conservation, because everything which we redistribute, so the sum of the relevances stays constant at every layer. So what we get the decomposition. This is what we originally wanted. We wanted to have a decomposition of the output. And we have it when doing it layer by layer. So we don't do it like in one step, but layer by layer by taking into account the activations and the weights. Okay, this is the idea which was at first born from our intuition. And later on, we thought about some theoretical framework which supports this rules. Or we didn't look for it, but by chance we kind of found a theoretical explanation for this algorithm. And this is a deep Taylor decomposition framework. So before we talked about Taylor decomposition, and I told you that it's a mathematician would regard the whole neural network as a function, and then would apply Taylor decomposition to it. Then you would find a root point which is meaningful, and then if you have a x tilde, so that f of x tilde is 0, you get a decomposition as a sum over all dimensions plus some higher order term. But when you ignore the higher order term, you get exactly this kind of decomposition. But as you saw, it's quite difficult, because it's difficult to find a root point, and also gradient shattering is a problem for deep neural networks. So instead, the idea is to do things layer-wise. So instead of explaining the whole thing at once, you explain layer by layer. And what you can imagine that in this figure, what you see is that you have classified the image, for example, and then you have redistributed the relevance until some point, RK. And then the question is how to redistribute the relevance to the next lower layer. You can either use some hand-designed, handcrafted rules, which I introduced here. These rules were born from our intuition. Or you can also do is you can view things as a function. You can view the relevance value RK as a function. And it is a function of the activations of the last lower layer. So RK only depends on the activations of the last lower layer. It is a complex function of these activations. Of course, it also depends on the weights, but the weights are fixed. So for every image, you can regard RK as a function of the activations of the last lower layer. And then once you have this formulation, you can apply this Taylor decomposition principle to this function. So instead of decomposing the whole thing, you are decomposing RK. And the key insight is that RK is a very simple function of the activations. It has this form, RK of A equals the ReLU, like max 0 weighted sum, times some constant, CK. This is a key insight of this Taylor decomposition work. We can also use this, and we can show this using inductive arguments, that this is the case for all the redistribution. But this is a very simple function, so it's very easy to explain it. It's very easy to find a root point. So here the root point is A tilde. It's very easy to find a root point for the simple function. And you also don't have any gradient shattering because it's just a ReLU. So you don't have any complex discontinuities like you have for the whole thing. So the idea is that you apply the same principle, the Taylor decomposition, but not to the whole thing, but to this relevance function. And you can show that for ReLU neural networks, this relevance function is a very simple function. Therefore, you can apply all these mathematical tools to it. And the cool thing is that, I mean, in this case, you have still the freedom of choosing the root point. So there will be many different root points which you could choose. Because what you want to have is you want to RK of A tilde equals 0. So you want to find an A tilde so that the RK of L tilde is 0. And depending on what criteria you put on the root point, you will arrive at different LRP rules. So we can show that these two rules which are introduced here are special cases of this Taylor decomposition framework using different constraints on the root point. So what do I mean by this? For example, if you have a ReLU nonlinearities, you know that all the activations are either 0 or positive, so that they cannot be negative. This AJ cannot be negative because it comes from a ReLU. Therefore, you may also constrain your root point to be positive or 0. If you do that, then you will arrive at a specific LRP rule. For example, if you have the first layer and you have a pixel, you want to redistribute relevance on the pixels. You know that the pixels, they lie between 0 and 255, for example. They have a box constraint. So you may also want your root point to lie in this domain. So once you do this, you will arrive at a different redistribution rule. And so on and so forth. So what we, over the years of our research, we realize that it's very important to apply the correct redistribution rules. Because, for example, for convolution neural network, for convolution layers and for fully connected layers, you should use different redistribution rules. And this deep Taylor decomposition frameworks tells you which rules are appropriate. So it's not like one method or one rule for all. You have to very carefully think what is a meaningful root point for a convolution layer? What is a meaningful root point for the input layer? And then you will arrive at different redistribution rules. And if you combine them, you will get very meaningful explanations. Sometimes what we see is people apply LRP in a very simple manner. They just apply epsilon LRP rule, like the simple naive rule, to all layers, and then they say, okay, this method performs worse than the method which I propose. But you have to apply it in a correct manner in order to have the full power of the method. And in our last book chapter, we kind of very carefully explained things. Okay, but this is about this best practice for LRP. Still, you may want to have to know which one to choose, because I mean, okay, we have this deep Taylor decomposition framework, which is very nice because it has some theory in it. You have some motivation, which is very clear, but still we need some criteria to evaluate and compare explanations beyond just looking at them. And there is actually a lot of work on evaluating explanations. People often, if I review papers, people often write, oh, we cannot compare quantitatively because there are no criteria, but this is not true. There is a lot of recent work on comparing and evaluating explanations. So one line of research, I will just very briefly go into it to give you some idea. One line of research uses pixel flipping, or what you do is you the idea is that you sort the pixels according to relevance, and then you destroy the most relevant ones and evaluate the prediction at this point. And then you measure the decrease. And the idea is that if your heat map is meaningful, then the classification score should decrease, because you would then remove the most important information in the image. For example, for the rooster, if you would destroy the rooster's head and have some random pixels on the rooster's head, maybe the neural network will not recognize this image as a rooster anymore. So this would be an evidence that this heat map is very meaningful. But this is only one criteria. Another criterion is like some axiomatic approach. People came up with different axioms. For example, one axiom which is very easy to understand, some continuity or continuity. So for example, if you have two images which are almost the same, so they're almost the same, and then you apply the neural network to them and you get predictions which are almost the same, then you may want your explanation method to produce explanations which are also almost the same, because you don't want to have some discontinuity. You want to have continuity in the explanations. And some of the methods which are on the market do not fulfill this axiom of continuity. For example, if you just use the gradient. If you just use the gradient, you may get very different explanations for images which are almost equal. This is a bad property. And you may come up with several of these kind of properties and then use these properties to compare methods. And sometimes you don't need to do any experiments. You can just, from the method, you can just prove that they fulfill some property or not. And very recent work, which we started recently, is using ground truth to measure explanation. Okay, so you may wonder, how do we get ground truth? Because in real images, you don't know. If you have the rooster, you don't know whether it's really the head of the rooster which is important, or maybe the feet of the rooster, or maybe the environment the rooster is in. So it's very hard to tell what is really important. Of course, you could do some human subject studies and then ask humans what do they find important, or you could also measure, for example, where they look at, and then have some human heat map, and compare it to the neural network. But this is very, this you can do, but this is complicated, and also may vary between subjects. So what we thought is that we construct our ground truth. There is this clever data set where you construct images and you have a question. So it's a visual question answering, VQA data set. So you can construct this image and ask a question. And then your neural network model will tell you the answer. So for example, here the question is, the cyan rubber thing is what size? You ask your model about the size of the object. And then you have, since you have constructed the image and you know where the objects are, you can create these masks and compare how good the explanation, the heat maps correspond to this mask. Because in order to answer the question, it's sufficient to maybe just consider this one object. For other questions, maybe you need to consider multiple objects, but you exactly know what is the important information to answer this question, and you can use this to evaluate your explanation methods. Okay, this was the first part, the method parts. Are there any questions to methods? If not, then we can also discuss later. I will tell you now about some applications. Maybe first, the highlight application, which I always show. There was this famous Pascal VOC challenge, 2005 to 2012. And the task was to classify images, 20 different classes, cats, cows, horses, dining table, and so on. And the best universities and research institutes participated in this challenge. And every year they compared the performance. Let me first explain this, and I will read the question. And at that time, I mean, people just compared performance values. They didn't have a clue what their method is doing. And what we did is we took the leading method, the method which won the challenge, and explained it. And we were really we didn't expect what we saw. For example, the leading method which won this challenge classified ships based on the presence of water. It classified trains based on the presence of tracks and rails. And it classified a lot of horses based on the copyright tag here at the bottom. So it didn't really look at the horse, but it had really good performance in classifying horses. And we thought, okay, how can it be? Then we looked into the data set, and over 20% of the horses had a copyright tag on it. This data set were automatically croned from Flickr, but it seems that for almost 10 years, a lot of high-class researchers have participated in this challenge. The organizers did a lot of work to get this data set, and nobody realized that this data set has a problem. A lot of horses have a copyright tag. And we kind of frame this phenomena as a clever Hans phenomena, and a predictor which kind of, instead of detecting the horse, detects copyright tags. We use the term clever Hans predictor. So in some sense, the best method was right in terms of performance, but it was right for the wrong reason. And in practice, if you would use this classifier in practice, it would perform really bad, because it didn't learn anything about the horse, but used an artifact to perform the task. And there is a famous example from science about clever Hans. The kluger Hans was a German horse 100 years ago in Berlin, I guess. And the horse was regarded as a scientific sensation, because people thought this horse can do math. It can count and solve math problems. So the guy asks the horse a question, for example, what is 2 plus 3? And then presented some possible answers. And in over 90%, the horse was right. It reacted on the correct answer. And only later, psychologists and other researchers realized that the horse was, of course, not doing math, but was carefully looking at the body language of the guy asking the question and presenting the answers. Because this guy was slightly more stressed when showing the correct answer. And the horse could see the difference in his body language. So in some sense, the kluger Hans was right, but also for the wrong reason. It didn't solve the math problem, but it just watched the body language of the guy asking the question. Similar to the predictor which we saw here. And we recently also had some article in the news and claimed that a lot of machine learning models out there are kind of clever Hanses. They didn't learn the correct thing. And people sometimes ignore it because they don't explain the strategy. And if we want to trust our models, we should explain what they are doing. Okay, so the question was, how common is the use of fuzzy systems as a method to explain what is black box are doing? I'm not so familiar of fuzzy systems, and I haven't seen any work on fuzzy systems to explain the predictions of neural networks, but I wouldn't rule it out. So I think there is still a whole community doing fuzzy research on fuzzy systems, and maybe they have published some work in this direction, but I'm not aware of it. Okay, so, but this was like the motivation example. Clever Hanses and detecting clever Hanses, but we have applied LLP to a lot of different problems beyond that, to videos, medical data, text, speech, and so on, and also to different types of models. LSTM, we have a paper together with Sepp Hochreiter on how to explain LSTM, clustering, one-class SVM, and so on. And I would like to present a few of these examples. Let me first give you some work-through examples. So also here we wanted to validate a phase classifier. So we there is a phase data set which you can download. It's almost 27,000 phases. The task is to predict gender and age. You have different age ranges between 0 and 2, 4 and 6, and so on. And we trained different types of models on this data set: CafeNet, GoogleNet, VGG16, AudienceNet, and we also played around with different types of pre-processing. And we kind of wanted to know what impact does it have on the prediction performance, but also what impact does it have on the explanation, on what the model is learning. And we saw, for example, here you see first an explanation of this guy. So maybe what I forgot to tell you is that we can not only explain the prediction, I mean, in this LRP, here we redistributed the correct prediction, the rooster, but we can also ask the question, what makes this image a cat or a dog? So we can redistribute relevance from the answers from the output neurons which were not the predictions, which are not the prediction. So for example, here we ask the question, what makes this guy belong to the class 0 to 2 years age? And you see that the red part is evidence which speaks for this classification decision. So the boldness of this guy, because he doesn't have hair, speaks for this age range, because babies also don't have hair, so it makes sense. But his face, his nose, his eyes, and his mouth have blue color, telling us that this area speaks against this classification decision. So a baby doesn't look like this guy. Also, like 25 to 32 years of age, we see that the face is okay. He could be in this age range, but the boldness is something which the model things is counterintuitive for this age range. Whereas for 60 plus, the boldness is okay, but there is some other negative relevance in the background. So you see that you can compare the heat maps and analyze them and see what the classifier is doing, how it functions. And here you have a comparison of epsilon LRP, so that's the noisy variant, this naive standard variant, and the one which we recommend. And you see that if you just use the standard epsilon LRP variant, the predictions are not very, the explanations are very hard to understand. So you should choose the explanation technique and the right parameters to get good explanations. Yeah, we had the slide before. And yeah, we can also, what we did here is we validated things. So for example, here we had a classifier which was pre-trained on ImageNet. So this is the second row. And the third row was a classifier which was pre-trained on an EMDB wiki dataset, which is a phase dataset. And you see that for this classifier pre-trained on ImageNet, there is a blue part on the mouth of this lady. This lady has been correctly classified as 60 plus, but apparently the classifier thinks that laughing is something which is very strange for old people. The other classifier, which was pre-trained on the face dataset, doesn't have this artifact. So you see here that even in both cases, the classification was correct. The features used in the ImageNet case were kind of clever Hans type, because apparently there was a bias which the model was picked up, that all people should laugh or don't laugh. Whereas the classifier pre-trained on this large face data set does not have this bias. So you can use explanations to unmask clever Hans examples. And we see here that if you pre-train on this EMDB wiki dataset, the performance also gets better. So you can iteratively, in some sense, validate the model and improve it. This is what I suggested before, where we can bring in human expertise into the development. Another example, we explained this model which was trained on this Atari games Breakout. So this was from DeepMind some years ago. They trained some reinforcement learning agent, and you see the explanations that on the left there was this. You can see from the explanations that the model was purposely building this tunnel, and it makes now a lot of points just by not without the risk of losing the ball. Very smart strategy. And a nice thing with explanations is that you can see how the strategy builds up over time. So on the x-axis of this curve, you see the training epochs. And the y-axis, you have the relevance of different elements of the game. The green line is the ball, the black line is the pedal, and the red line is the tunnel. And you see that the first thing the model learns is to focus on the ball, which is a very smart strategy, because if you lose the ball, then you lose the game. Then the second thing is to treat the pedal as a relevant feature, which makes sense because you need the pedals to control the ball. And only after 50 epochs, it finds this tunnel building strategy. So you can use the relevances to understand and analyze the training process of a neural network, visualize learning behavior. You can also compare different architectures. For example, here we compare different architectures. the training behavior of different architectures, or also like different replay memory sizes in all cases, so you can compare parameters or meta parameters using explanations. Okay, so this was like some motivating example. Now I will come more into what we do is in now state of the art, which is very recent. So we thought, okay, LRP gives us this individual explanations for individual predictions. But it would also be nice to have some general view on the model. What are the most common prediction strategies? So what we proposed is it's called SPRAY, spectral relevance analysis. We propose to cluster explanations. And then you have a cluster of explanations. And this will tell you like what are the most common strategies of the model. So for example, here we see that for the horses, there are two clusters which use the copyright tag as a prediction strategy. There is one cluster which use the hurdles, and there is another cluster which is more diverse. So you can, instead of going through all the heat maps manually, you can cluster them and just look at the cluster representatives to get an idea of what you get. So we use spectral relevance, spectral clustering. I won't go into detail too much here. It's a standard clustering method. And the nice thing is that in spectral clustering, you can analyze the eigenvalue spectrum, and then you see how many clusters you have. The question was, do you produce the same kind of time graphs in supervised learning, looking at how factor? I mean, you could also like cluster things over time. I mean, here we just kind of summed up or compute the mean relevance over this. So we kind of tracked the ball and computed the average relevance on the ball, on the pedal, and so on. But you could also use some more advanced clustering techniques. But I think for the simple game you don't need it. But for real images you need some more clustering. But anyways, what you see here is that for this data set, a neural network was trained to classify airplanes, and there are two clusters. In one cluster, the network is really detecting airplanes. In the other cluster, you have a lot of boundary pixels which are relevant. And apparently, what we realized later, this artifact came from the fact that we used some padding for these images, because these images were from the Pascal VOC competition, and they were not square. So they had a shape which was not square, but the neural network only accepted square images. So we had to do some padding. And this padding produced some artifact for the airplane class, because you have a lot of sky borders. And if you pad the pixels, then you have a lot of areas with no structure. And apparently this feature has been picked up by the classifier. And if you destroy, for example, if you put random color on the boundaries, the classifier score goes down. So you see that even this kind of very standard pre-processing, like padding borders, can lead to artifacts. So, and we would not realize it. We wouldn't realize it by just looking at the predictions, because the predictions look okay and the images look okay. There are no copyright tags, but the padding artifact has been picked up. So you need explanations to get some insights. Okay, then we thought, but I mean, it's quite time consuming to analyze these clusters and do it all by hand. So we thought, how can we speed it up? How can we scale it? So for example, if we want to apply it to ImageNet, how can we scale it? And this is what we did in our very recent work. We kind of used, in this embedded space, we use some automatic method. FDA, Fisher's discriminant analysis, is just a linear classifier, which where we use these projection directions to get scores which tell us if there are outliers in this embedded space. Because here you see that there is a blue cluster, which is a lot of inliers, and there is a green cluster, which is slightly away from the majority. So it has some, the green cluster has some features which are not in the majority of the images. And we wanted to identify this kind of strange looking heat maps also in ImageNet and in larger data sets in an automatic way. And we saw for here this stability scores. We saw for the class laptop there is a large value, and also for some other classes. And for example, for the class laptop, you see in this you have the embedding, and you see that there are some red points, which are the outlier clusters. And you see that these images belong to a laptop which was taken in the same position. So some of the laptops in the ImageNet dataset have exactly the same position. And apparently neural networks, they just remember the position and use this for classifying these images. So this is something which you don't like to have. Similar for the jigsaw puzzle. So there are some images of puzzles which look exactly the same. So the shape is exactly the same, only like the background image is slightly different. But also here the network just remembers the shape. So it doesn't care if it's puzzles or not, but it remembers the thing. So also in ImageNet you have copyright tags. So there's this class truck, which has some copyright tags. And yeah, and it's very hard to identify such problems in large data sets, because you cannot go over a million of images by hand. Even if you would, you wouldn't remember. And we can identify these problems in an automatic way by using the model as a filter and using our technique to visualize problematic cases. And of course, what you want to do is you want to go beyond. You want to enhance. You want to enhance ImageNet or de-hance. And what you could do is you could, for example, if you have a copyright tag like this, and you don't want your model to focus on this copyright tag, you can just add a copyright tag to some other images, to make some fake images with this copyright tag, and this will lead to the fact that your model is not using this feature anymore. So this is one simple way of enhancing your model, or enhance. Yeah, that's also nice. And this is how it works. I mean, you see that after some epochs of fine-tuning, the copyright tag was not used by the model anymore. And we are still in the process of writing things up and having like this enhancing or enhancing on the ImageNet scale. Similar features here. Okay. This was one very recent work. Another one is some explanation guided training. Enhance, yeah, that's right. That's good. Enhance. Here we want to enhance our training. We want to enhance without Hans our training, and the task is a special task. My colleague is working in this cross-domain few-shot classification task. So we have some you have some image, some query image, for example, an image of a dog, and you have some support images with labels. And what you want is to have the prediction for this image. And yeah, I think people use some complicated models for that. But what we did is we kind of use the CNN to extract features from the source images and also from the query images. Then do some feature processing. This is what you do anyways. But the trick, what we did is we added some additional loss, which not only, I mean, you have the standard loss between the prediction and the true label. And we also, like, what we did, we use the heat map. We use the heat map of these images with respect to this class labels to filter the image. So we have kind of so we use the heat map as kind of an attention module. And so we filter the features FP with the heat map and give it as an additional feature, and have it this additional loss term, which kind of measures kind of the deviation between the true label and the one predicted only on this filtered image. So it's kind of similar to like an attention, but for attention we use the heat map, and we get better results than the standard technique. But details you can check in the paper. Another very recent work where we are currently in revision with that is XAI-based pruning. So with LRP you get relevance values for every neuron, not only for the heat map in the end, but for every neuron in between. Because I mean, you have this picture. Yeah, so you have this relevance values for every neuron. So what we thought, okay, why not use these relevance values to prune our networks? Because we know which one are relevant and which are not. So we can use XAI-based pruning. And especially in a case where you have a big neural network, like trained for 1,000 classes, but maybe you want to use it just for a subset of classes, and you want to prune filters and neurons which are not relevant. And it works very well. It works. So we compared it to other types of criteria, like just using the weight or Taylor or gradient, and it works much better in these examples on a couple of different data sets. Okay, maybe another type of applications in the sciences. I just want to give you an idea what we could do with these techniques. We applied it to fMRI signals. These are very high dimensional data sets, and got like explanations for every prediction. And the cool thing here is that usually if you study fMRI, you compute p-values between two groups. So you compute, for example, p-values between patients and healthy controls. And so you have your kind of you have your significance values on a group level, but what we get is explanations on not only on a group level, not only on a subject level, but for every trial, and even for every measurement, for every time point, we get a heat map. Because what we put into the neural network is a fMRI volume, and for this volume we get the heat map. So we didn't do it, but this is something we want to definitely do, is to study the flow of relevance over time. For example, we can see what is relevant in the first few seconds of the experiment, and what is relevant in the later part of one trial. So we can study variations of a trial within one trial with these tools. and you cannot do it with standard fMRI analysis tools. So usually these fMRI studies, they only compare groups of people, and here we have a much better resolution. We can study differences between individual participants, and we can study even the variation within one trial. And with our friends from neuroscience, we hope to get some good insights with that. We also applied it to some other types of scientific applications. I will not go too much into it here, but the idea is to show that with heat maps you can detect biases in the data, and biases in sampling, and biases in class correlation. So when training classifiers for the scientific applications, you can run into a lot of troubles, a lot of biases, a lot of problems. And in this work, we show that using explanations helps to uncover some of these problems. Okay, this is the last topic of today, and we will have some time for questions. Beyond explaining classifiers, this is something which I find also very interesting, because a lot of machine learning models are not, or problems are not classification problems. For example, clustering. And what we propose is to do this, because we know how to explain neural networks. We know that. I have shown you there is also some theory around it, but we don't know how to explain, for example, k-means, or we don't know how to explain other types of algorithms. So the trick is, we call it the neuralization trick, is to convert your solution, your clustering solution, into a neural network, and then you can apply the whole machinery which we have. Then you can apply LLP because you know how to apply it. So you kind of map your algorithm or your solution into a neural network, and then you can explain the solution. So here in this work we showed how to construct, given a clustering, you can map it into a neural network. You can, for example, construct a neural network which tells you what is the evidence that this image falls into cluster C, FC. If the output is greater than 0, then this image would fall into cluster C, otherwise not. So once again, to be clear, we are not clustering anything here. We have applied our k-means. We have the clusterings ready. So we have finished our clustering, and then we want to ask the question, what makes this data point belong to cluster C? So for that, in order to answer this question, we construct a neural network which is equivalent to the clustering solution. So this neural network is kind of equivalent to the clustering which you have. Yeah, and you can explain it. Here what we did is we clustered intermediate features of the VGG model, and saw, for example, similar, saw that in some intermediate layers, in the lower intermediate layers, you have a lot of edges and shapes and textures which kind of belong to one cluster. So a lot of activations which kind of belong to this cluster, whereas in higher layers you have more abstract objects. But in principle, you can apply it to any types of clustering you're interested in, and you will get the answer in terms of what is the important feature which makes this data point belong to cluster C. This is what we want to answer. Yeah, conclusion. I have recently organized an ICML workshop on extending explainable AI beyond deep models and classifiers. I think this is exactly the topic which is very interesting. What to do beyond just explaining, because there's a lot of work on explanation methods. There is theory, there is a lot of different methods, there is a lot of different evaluation techniques, but the key question is how to improve your model automatically, or how to enhance your data set or your model automatically, how to prune your model, how to get insights in scientific fields. And this is one line of work which I'm currently doing. And in the other line is how to extend these concepts to other types of models and other types of problems. And yeah, this is it. There is a lot of papers which describes this work, methods papers. Yeah, I will share the slides with you, but we have published a lot on all these topics. Here we also find the book, which is a summary of ongoing work, not only from my group, but from many other groups in the field. And we also have a homepage, heatmapping.org, where we have some tutorial software and a lot of, and also the papers which I listed are also there. So if you are interested, yeah, you can check it out. Otherwise, let's have some discussion. I think we still have some time for discussion. Thank you very much.
Thank you very much, Wojciech, for the very interesting presentation. It was extraordinary, let's say, review and tutorial. We have some minutes for discussion, so maybe there are some questions from the audience. So please write your questions in the chat, or you can also turn on your microphone and video and ask a question. There's a lot of congratulations.
Thank you.
Oh, yes, there is a question.
Yes, on this fMRI results, sure, I'm very happy to do that. So, yeah, first we had the first task was to train the model, because fMRI has a lot of dimensions. So we took a whole brain approach. So we put the whole voxel into all the voxels into our neural network. And in order to reduce complexity, we did it, we kind of sliced the brain into slices and analyzed each slice using a CNN, and then used an LSTM to integrate spatially. And the task was here on a decoding task. So it was this human connecticum data set, a large data set of fMRI. And what we did is we kind of explained, once we had the output a prediction, we could go back through the LSTM, through the CNN into input space. And the input space was a single volume, a single fMRI volume. So the prediction was the decoding, and the explanation was for every voxel you got a relevance score.
Oh, there is, thank you. So, okay. Is there any other question?
I think this is like a very fast moving field. So there is still a lot of things to do. Okay, yeah, for regression. This is an interesting question, like for how to explain regression. I think if you think about other types of problems, you really need to think about what does the explanation mean in this context? Because for classification, it's kind of more or less clear what we want to have. If we want to have a decomposition of the prediction score, so that we know like which features have contributed how much to the classification. So from the methods point of view, there is no restriction. So you can also like apply it to regression problems. That's not a problem, but you have to take care that the explanation you get, you kind of know what it means in this context, because in regression context, it can mean is something else than in the classification context. So you really need to think about what does this explanation mean for this problem or for this type of problem. But I think there is not so much work on applying things in regression, but still I think some people did to apply similar methods there, but I think there is still some room. Or are heat maps always interpretable by humans? No, they are not. I think this is something which is also very important. There is an interpretation gap. So for images, I would say it's maybe kind of often easy to get the idea, but also not always. But for images, we have especially if there are objects present in the image, so you can correlate what you see to the object. But from other data types, for example, if you think about a time series, or if you think about an image of on kind of, I don't know, about some radar image or some kind of data which is some kind of sensor measurements which are hard to interpret for the human, there also it's very difficult to interpret the heat map. So there is this interpretation gap. And so also one goal of our research, but I think many people are nowadays interested in to make explanations more abstract, to more easy for humans to comprehend and to interpret. But still, I think there is lots to do. Semantic segmentation. I've seen some work on segmentation, but also there, I think you have to be aware what you make out of the results. If you have just a segmentation, I mean, what would you expect? Would you expect to have relevance outside the segmented objects, or would you have, I mean, so I think in these problems, sometimes it's not so easy to have some meaningful case, or to make a meaningful case that you say, okay, maybe this cells have been segmented in this way because they have some boundary feature. I think in many other applications of segmentation, it can be difficult to make a good strong point. But I think there is still room for it. Yeah, with the toolbox, I mean, we have this Keras toolbox. We are currently working on PyTorch toolbox. So it's, as I said, I mean, you have to, it's always good to be aware of what these methods are doing, because sometimes if you just have a toolbox and just press the button without knowing anything what you are doing, then maybe you may use the wrong rules, or you may explain something in the wrong way. So we are trying to make these things as easy as possible, but still, I think also in this explainability research, is good to know and to understand what you are doing. Yeah, I mean, this is a vulnerability to tiny changes. So yes, I think, I mean, explanations are vulnerable in the sense, in the adversarial sense. That's true. That's true. And but what I meant here in this axioms, I think it was even more it was even more tiny, like so you can formulate it in the limit. Things are discontinued. You can study like discontinuities also, like in the limit, when things become very, very small, and gradient based approaches have a discontinuity. So even if you make the two images as similar as possible, you may get a discontinuity which you don't get in the LRP case. but still LRP, and also I think all methods are vulnerable to adversarial examples. So I would say that adversarial examples is something which is still a big problem in machine learning, but also like on deep learning, but also in explainable AI. So it's still, these things are still vulnerable. The working example. So we have they are from the paper, from our recent paper, which is under review, but we have it on archive. And this is like this one, interpretable machine learning toward interpretable machine learning, transparent deep neural networks and beyond. With the video games, I think that I've seen a couple of papers on Atari games or video games where people use interpretations. I think if you look for them, you will find them. There are a couple of them around. Yeah, our work was published in Nature Communications, where we kind of analyze this game, but you can certainly also analyze other types of games, and also like a representation of the network. So I don't really understand the question with the S and P values, but okay. I mean, this is like the one is the source image, because this is a very special task. This is a cross-domain few-shot classification task, where you have like one query image, like an image of a dog, and you have example support images with a label. And what you want to kind of find out is, I mean, in the end, you want to classify this image as a dog based on the information from this support images, because these are dogs and they look similar. Therefore, you want to classify this image as a dog. And therefore, you need these two networks. You need a query network and the source network. So here comes the source images, and here is a query image. And you kind of put it in to concatenate and then classify.
We still have 7 minutes, so there are some questions, maybe more questions. But I have one, maybe more philosophical questions. What do you think about, let's say, future explainable AI systems can be used, for example, to evaluate human decisions? So, for example, in the medical domain, we can get maybe in the future the result of the intelligent system, that there will be, of course, a diagnosis and the reason for this diagnosis, which will be a product of the system. And then such kind of, let's say, reasoning can be used against the human, let's say, reasoning. What do you think about such kind of comparison?
I think, I mean, what you can imagine is like a backup system, or like a second opinion system. I think people are already working on this kind of systems, that you have maybe the medical expert who is responsible and who has his opinion, but you have maybe some second opinion support system, which so it's not like against, but it should support the human expert. But also with that, I think there are some studies which study the behavior of people having such support system, because sometimes if people are using such support systems, they can be overconfident, or these kind of systems can lead to behaviors or decision behaviors which are not wanted, for example, because people maybe then think, okay, we have a AI system, and the AI system is saying, okay, this is this type of disease, and even it has some explanation. So I think in the end, it's very important to optimize the interplay between both the human and the machine. But also, like, this also includes like having certain criteria for the human, how to do things, how to react, how to interpret the information from the machine. Because if you don't guide the human, then the human may also be may use this information in the wrong way.
Yeah, actually, they are doing now using, let's say, very simple, just presentation of information in internet, and maybe in the future there will be some kind of solution that, let's say, intelligent systems will teach people using such kind of, let's say, reasons and explanations, and that could be very dangerous.
Yes, because I mean, these systems, they learn from data, and they are not intelligence, and they just learn from data, and if the data is biased, if the data is wrong, if there are some problems, then they pick it up, and for example, you don't want to teach humans use these kind of systems which are not 100% correct, or which are vulnerable to adversarial examples for teaching. So I think in the end, you have to optimize the interplay, and this is a whole research area, I think, how to optimize computer-machine interaction and how to do it in a clever way.
Trustworthy AI, which is the, let's say, the headline from the European Union, I think, in every document.
Yes. I'm now involved in some writing a proposal grant for a project on trustworthy machine learning.
Okay.
Because I think this is a hot topic nowadays. Yeah.
Yes. Okay, so maybe we have time for one last question from the audience, because there is something in the chat window. So maybe Wojciech, you can try to.
What kind of variables are required to be able to measure relevance over time of different components? I mean, in this case, in the games, I think it's very kind of easy, because it's very restricted environment, right? You just have the game, and the window doesn't change. The background is very simple, and it's very easy to identify the ball in every frame, so you can very easily capture the relevance. If you want to measure like relevance over time, for example, for ImageNet type of classifiers, it can be more complicated, because it can be more difficult to understand what we are measuring. Here we have just a few elements. We have the ball, we have the pedal, and it's very easy to make sense of it in this strategic game. But for real life data sets, it can be much more difficult to identify this relevant these different components.
Okay, I think that unfortunately we have to stop now, and I would like to say thank you very much, Wojciech, for this really extraordinary presentation and very, very interesting discussion. And I would like to say that maybe we will meet again next year or in 2 years. So once again, thank you very much for your support and for being volunteer for our summer school. So thank you very much.
Thank you. Bye-bye.
Bye-bye.